Okay, bridge students, we have a lesson today about proving that lines are parallel. Our last lesson looked at parallel lines and then made a bunch of deductions about the measures of those lines based on alternate interior angles and corresponding angles and same side interior angles. You'll remember that. What we have now is the converse, and my objective is this. Students can use the converses of parallel line and transversal theorems, again, those same theorems I just mentioned, to prove that two lines are parallel. So we're going in the opposite direction. What I'm going to do today is talk first about the reasoning pattern. What is a converse? And then I'm going to get into kind of a more technical problem. It deals with some interesting visual issues and some issues with systems of equations that I think are good technical issues to work with in terms of what we're doing here with distance learning. And so, first of all, the easy part, conditional statements and their converses. So a conditional statement is an if-then statement. I'll use my famous hot pink color. If P, then Q. For instance, with the alternate interior angles theorem, it would be that if two lines are parallel, then they're alternate and they're cut by a transversal, then their alternate interior angles will be congruent. The converse is the opposite. If Q, then P. So in this case, if alternate interior angles are congruent, then the two lines that form them, that are cut by a transversal, have to be parallel. Okay, this is a special kind of statement, something that works as an if-then statement and as its converse. In math is a very special kind of statement. It's called an if and only if statement. We're not going to get too deep into IFF or if statements here, but they're important to think about. You could represent it like this. The arrow goes both directions. Not all conditional statements are like this. We can think of the zebra example I gave way back in our opening. So I think if I remember correctly, what I said was that if it is a zebra, then it has black and white stripes. So I want you to think about that. Is the converse of that true? The converse would be, if it has black and white stripes, then it is a zebra. And you may think of other animals that have black and white stripes. So I'm pretty sure that would not be an IFF statement, an if and only if statement. Okay, so the main idea here is that we understand what the converse is. All right, so now I thought I would give you a fun, kind of gnarly little problem, a difficult problem. It says, determine the values of x and y required to show that both pairs of lines, A and B, those are the ones marked in brown, and M and N, those are the ones marked in blue, are parallel. And maybe this is actually not so bad, because we know that from the converse of the alternate interior angles theorem that we can say this, that if the two angles marked in brown here, if 36 equals 3x plus 2y, if, I'll put it the other way, 3x plus 2y equals 36, then we know that line A is parallel to line B. Now to look at the other two angles here with lines M and N, those are the ones in the blue. You have to kind of like turn your head sideways. If I turn my screen sideways, it's kind of, it just flips again, so it's hard to see. But if you turn your head sideways and just focus, imagine almost that the brown lines aren't there and look just at the blue ones, you'll see that the angles I've marked out here, 12x plus 2y and 126, are corresponding angles. I want to look at that for a sec while I write this down. If 12x plus 2, there should be a y here too, y, plus 2y equal 126, then m is parallel to n. So something that the Go Math 8 book does not do well is work with systems of equations, which is one reason I picked this problem. I think we need to practice systems. So to solve this situation for two variables, we have to solve what's called a system here. I'm going to get my drawing tool back. I'm going to try to draw a little bit better here. Oh, if I go too slow, it does that. So we're just stuck doing this. 3x. Actually, I'm going to go this way. I kind of setting up the system sometimes takes some thought. So here we go. I'm going to put the other equation on top. I'm going to put 12x plus 2y equals 126. And then we have 3x plus 2y equals 36. Now, there's I would say at least three ways to solve these equations, but and find x and y. But the most convenient way here is going to be what's called the elimination method. And the idea here is you have to notice the statement that 3x plus 2y equals 36. So 3x and 2y, that whole amount is the same thing as 36. And so if we subtract 3x and 2y, 3x plus 2y, from the left side of the first equation, and subtract 36 from the right side of the first equation, then by logical deduction, we're going to end up with a true statement. And so let's go ahead and do that. 12x minus 3x is going to be 9x. 2y, might take away 2y, is nothing, so we're just left with a 9x, and 126 minus 36 is 90. Okay, and if we're struggling with this a little bit, don't worry too much. This is really underemphasized in the Math 8 book, or really the Math 7a book. There's more on it in the Math 8 book, but you guys didn't get that. Okay, so we're going to make a 1 here. I'm going to find that x equals 10. And the way to figure out what y is you put the value for x back into one of the two equations. I'm going to pick the easy one, the 3x plus 2y equals 36. I'm going to say 3 times 10 plus 2 times y equals 36. We get 30 plus 2y equals 36, and 2y equals 6, and y is going to be 3, which means that our solution to our system here is 10, 3. So more can be said about that, but that would be, I want to go back to our original logic, that if we plug in 10 and 3 for x and y into the first statement here, if 3x plus 2y equals 36, then a is parallel to b. Let's see, 3 times 10 plus 2 times 3, yes, that equals 36, and so a has to be parallel to b. By the same logic, 12 times 10 is 120, plus 2 times 3 is 6. It does equal 126, and so m is parallel to n. Fun. There will be more problems for you working with the converse of all these parallel line theorems, and I hope you have fun with them. Thank you.